Good afternoon, dear student, and welcome to this other edition of our Numerical Method 2 class. Before I proceed, I would like to inform you that your marks, when I say your marks, test 1, test 2, the assignments, by tomorrow afternoon, let's say by tomorrow evening, I will make sure that I release all the results so that you will know what you need to perform for the comprehensive test. Yeah, because after the comprehensive test on Friday, there will be another test. That will be the makeup test or the supplementary test on the 19th. So exactly 1 week later on, that is Friday next week. Yeah. So that is it. And in terms of the test, comprehensive test, what we'll be covering from today is not part of the test. So the test will stop, the scope will be up to the QR decomposition or QR factorization. How's other method, the one that we are going to tackle very soon, is not part of the test because you will not have enough time to assimilate, to master, and to understand and try to solve problems, since we are writing on Friday. That will only be considered, or will be part of the scope of next week test. That is the supplementary. So I repeat, House orders method and Jacobi are still to be covered. So they are not part of the scope of the test this coming Friday. But instead, they will be part of the makeup test or the supplementary test. Okay, this being said, without any further ado, let us dive into the subject of house orders method. As I already mentioned last time, for the house order method, we use house order method to find a symmetric tridiagonal matrix. That is, we are given a matrix A. Okay, what is when are two matrices similar? Let me quickly recall that. That's something you did in linear algebra. A and B are similar. If we can find a matrix, an invertible matrix P, invertible matrix such that A can be written as P, B, P inverse. See, that's why you say invertible. So if you have something of this form, these two are similar. Now, in terms of the house order method, if I have a matrix A, obviously you assume that A is a symmetric matrix, right? Now, house orders method will find this B, right? From A, you get the B, where B now is tridiagonal. So that's the main purpose. You have something of this one because they are similar. Symmetric matrix B that is similar to A. So this B will be symmetric and tridiagonal. And we have that. So we are able to find a P and invertible matrix such that A can be written in this form, where B is symmetric, tridiagonal. Obviously, A also is symmetric, right? Okay, so that is roughly speaking Householder's method, nothing else. Now, in order to get this B, we are going to go through a series of construction. We are going to build, we are going to construct the matrix that will allow us to transform A to B that satisfies or that has these properties. Okay, so before that, we are going to define what we call the Householder's transformation, because we are going to transform this A in order to get a tridiagonal, right? So now, how do we construct the transformation? Remember that we constructed G, Ij, that we perform, we apply to A to get R. It's something a bit similar. So we are going, you know that we perform many transformations on A until we obtain our upper triangular matrix. So it's something a bit similar, not exactly the same, but similar, that we are going to do here. But you will see, you understand how that works. Okay, first of all, if you have a vector in Rn, right, that satisfies this. In fact, this means that W is a unit vector. That's what it means, right? It's a unit vector in Rn, because remember, this is a dot product, and the norm of W, this is nothing else than the square root of this, of that dot product. If this dot product of W with itself is 1, it means that the norm is also 1. So this is equivalent. So it's a unit vector. So you take W to be a unit vector in Rn for the two norm, of course. I mean, unit vector for the two norm, of course. And then from this W, from this unit vector, we construct a matrix. Isn't it not surprising? Isn't it surprising? It's surprising, eh? Look, I take a vector. Here we have the dot product equal to 1. But if we change the position of the transpose, take it like this, it gives us a matrix, n by n matrix. Here we have a number, but here we have a matrix. You see that the position of the dot product, I mean the transpose, will change everything. Just linear algebra, you can check it from linear algebra. You will see that if I take this and that, it will give you n by n matrix. That is metric multiplication. A vector is a matrix, right? A vector is a matrix of size n by 1. So if you use that, you will see that actually this will give you a matrix. So this is how we construct Householder transformation matrix, or transformation or Householder matrix. From a unit vector. Okay, see what is happening here. You remember the way we constructed G, right? Let's say Ij here, theta. If you recall the way we constructed this, we took identity, we modify identity. The identity matrix. So we took the identity matrix and we modify it. You see, we have the same, it's the same scenario here. You see that we have identity matrix and we modify it. So when you say we modify, we append or we subtract. Appending or subtracting is the same. So we have the identity matrix, and then we add something to it, or we subtract something from the identity matrix. So we are still modifying the identity matrix. And what do we subtract from the identity matrix? 2 times the product of W with its transpose. And we obtain this transformation. Okay, I hope it is clear. There are some analogies. There are some few analogies, but not exactly the same. There are a few analogies. Now, here we have this result that the house order transformation given above is symmetric and orthogonal. We know already what it means to be orthogonal, right? We know what it means. We know also what it means to be symmetric. That is, if I take H transpose is the same as H. That is symmetric. Now, to say that is orthogonal means that is equal to the inverse, or which is equivalent to H transpose H is the same as H transpose equal to identity. That's what this means. Okay, so we are going to try, we are going to check this. We are going to check this. You see that this fact gives us symmetry, right? Why? Because if I write H transpose, what is it? It is identity minus 2 W transpose, like this. Now, if I expand this, this will give me identity transpose, which is identity minus 2 W transpose transpose. And this W transpose transpose is exactly what we are doing here, and we obtain that. So if I use this result, I can say that will be equal to identity minus 2. Now this is equal to W transpose. And what is this? This is exactly H. So symmetric. Okay, now we are going to use the fact that W is a unit vector to show this, that the transpose H into H gives us identity. Obviously, you have to do on the other direction, but okay, so we take H, we multiply by its transpose. So we know already that H, by definition, is this, which we put here. Now, time is transpose. We know that H transpose, because it's symmetric, is H, right? We use that result, and that's what we have here. And now we expand this, that's the product, two matrices. So you expand this, so this first I is I times I, which is I. And then we take I into this, negative 2 W transpose is the same, because I is neutral, right? It's identity. And then we take negative 2 W transpose into I, it gives us negative 2 W transpose. Now we multiply negative 2 W transpose by itself here. So that would be 4 W into, okay, so let me write that. So here we have negative 2 W transpose, W transpose. So this is 4 because of the negative. Now, Can take this there, then we are left with this W, right? And then the next is W transpose, and then W transpose. So you see that this is what we have. Now we can group these two like this, and we know that this is 1. So this being 1, we are left with 4 W transpose. So here we have the transpose here. Okay, so that is for this last expansion. So we have identity. These two will be -4, and plus this 4, they will cancel out, and then we have identity. Right, so this into H transpose is identity. Similarly, if you take H transpose into H, it's still the same because H is H, right? Right there, it gives us the same. So this being equal to that, this is what it means. So H is orthogonal. It's good to know this property. If you recall that orthogonal matrix, we don't need to compute the reciprocal, the inverse, sorry. We don't need to compute the inverse of the matrix. What do? We just take the transpose. So that's what is important. Okay, as I said, there's a transpose here. Okay, so we have that property. Okay, now the next thing to do is to see the effect of this transformation on a matrix. Because remember our goal is to transform A into a matrix that is tridiagonal, that's symmetric and tridiagonal. Now, and that's what we attempt to do here. Right? We first try to perform some transformation and see how that transformation will affect the entries. If you recall what we did with Gibbons rotation, we took a column in the matrix, we perform our transformation in such a way that not all the elements, but because we are in 2 dimensions, like this, 1, 1, and then 2, 1. We perform in such a way that this is transformed into an entry here, a non-zero entry of, in fact, an entry, not necessarily 0, and this is necessarily 0. So we are going to do something similar because we want at the end to transform A into a tridiagonal. Tridiagonal means that there will be only 3 diagonal like this. Like that. If it's tridiagonal, it means that in the first column, the first is an element that is not necessarily 0, and all the remaining entries here are all zeros. Oh, no. It's not like that. I didn't do that properly. Tridiagonal is like this instead. It's like this. Meaning that we have 2 here, right? 2 here. And the remaining here are 0. And then we have 1 here. And the remaining here are 0. So 1, 2, 1, 2. Similarly here, 1, 2, 1, 2. Oh, sorry. So here we have 1, 2, 1, 2. Like here 1. Anyway, so that is the purpose. So we will try to follow something similar. So that's why here now you see that when we apply our first transformation to the first column, you see that this is unchanged, and then we have the second one because there should be 2 elements, A11 alpha, and then from the third position to the last, everything is 0. Right. So that's the idea. And by performing this, it will give us the values of our W, because remember we need to find how our expression of the of H, I mean the H, because remember H is defined by W, right? H is defined by W, right? If you look at H is identity minus 2 W transpose. So I need to find W define H. So if I want H to perform something, I will write whatever, but it will have an impact on the values of W. Exactly the way we did with the Gibbons rotation. The idea is similar. Okay, so here, this is for the first transformation, because remember that even with Gibbons rotation, we have the first multiplication, and then the second, and so forth until we reach the final result. That is, we zero all the elements below the main diagonal. That is for the Gibbons rotation. But here in our case, we'll be zeroing the element in such a way that we obtain a tridiagonal matrix. But now the advantage here is that because our matrix A is symmetric, each entry that I zero will be 0 also symmetrically. Okay, let us look into that. Okay, so the first thing is to get H1 in such a way that you see H2 here. I mean A2. Remember that these matrices have to be what? Similar. They have to be similar, 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 similar. So when I take A, I perform this, because remember that this one is a transpose. Remember the definition, we say that A should be equal to what? P B, where B is the tridiagonal. I will change that into T, so that it will recall you that it's tridiagonal. I will put T here for tridiagonal, and then P inverse, right? Okay, but now this, in our case, it will be something of this form. Now we'll be using those rotation to be our P, and we know that they are invertible. Why? Because they are orthogonal. And then we get something here, and then we get the transpose, something like this. Because we know that H transpose is H inverse, right? Is the same as H inverse, right? And we know that H transpose is H. That's exactly what we wrote here. H transpose or H inverse, they are all the same. So that's why here you see this. We just rewrote this as HTH, right? Okay, or we can see right, it's still the same. You see that if I take H and multiply on both sides, This is still equivalent. Instead of writing A equal to this in terms of T, I can write T in terms of A. So this is equivalent to T, oh, sorry. So that is equivalent to T equal to H, A, H. You see. Okay, now, for the first time that I perform this is called H1. H1. And the result that we obtain, our T, because this is not the final T, right? Because in the process, I will be zeroing until I get my final T. So in the process, this will be called A2, right? So if I apply for the first time, the approximation to T is what we call A2, and that's what we have here. So A2 is an approximation of T. It's not yet the final T. I'm still zeroing. It's at the end that it will obtain a full tridiagonal. So that's why you have this notation. It comes from the similarity, this one. That's where it comes from. So I'm explaining all this so that you will not get confused and you understand every statement here in the note properly. Right. That's why I'm taking all this time to explain. Good. So that's what we have here. The first time that you perform the transformation, you get a transform A, which is not necessarily the final T that we are looking for. Right. Okay, now in A2, we have this, all the entries from the third position, you see, from the third position to the last, all these entries are 0. And because all our A's are also symmetric, by the symmetricity property, these all the entries will be 0, meaning that, let's say we have alpha, theta, gamma, delta, right? Something like this. Let's say that we have that, and we have, okay. Anyway, that's not really important, but let me leave it. We have this, because it's symmetric, I will put, if this entry is A, we also have A here. If this is B and here, this is B and C here, because it's symmetric, we also have B here and C here. A, B, C, D, E, F, right? Similarly, what will we have here? We have F here, E here, and D there. You see, that's what it means to be symmetric. This is equal to that, symmetry about that. Okay, now if I zero this entry from the third position, if I zero this, as I'm zeroing this entry, this will also be 0. As I zero this will also be 0. You see now, you see the pattern. And when I will zero this, this E will also be 0. And now what are we left with? You see that this is tridiagonal. I have this diagonal, this main diagonal, and this other diagonal. Sorry. You see, that is tridiagonal. So what I do, the first time I zero the entry in the first column, and then the entry here in the second column, and so forth, until I obtain a tridiagonal matrix. So I don't need to concentrate there on top. I need to concentrate here, because each time I zero elements here, you also zero the other one because of the symmetricity of the matrix or the operation. Because remember that we multiply A to the left and to the right. So when I eliminate here along the column, you also eliminate along the row. This is the column. Here in the column, you also eliminate in the row because of this multiplication on both sides. It comes from there, nowhere else. You can even use MATLAB or Python and try to perform elimination. You will see that if you multiply a matrix to the left or to the right, you have different effect. But if you multiply on both left and right, you see that it will perform a simultaneous effect on the matrix, exactly the way we have just observed. So that's roughly the explanation that is given here, right? Okay, now you repeat the process many times until we obtain a tridiagonal, right? This one, this is the final. You proceed until you obtain a tridiagonal matrix. Right, now let's see how we will be computing our W, because that's the main purpose now. How will we obtain the W that will allow us to obtain such result, to zero the entries? Right, so now that's what we are going to do. First of all, W is a unit vector. Right, and because it's a unit vector, and that, because here we want to see how to construct H1 such that A2 will satisfy this condition, right? That will impose n condition on the entries of W. Remember, W is an n, is in Rn. W being in Rn has n components. W1, W2, up to Wn. So these are the entries of W. So we need to impose conditions on this and solve and obtain a system or something that would allow us to get our W's. So that's exactly what we will be doing. All right. Obviously, this is a choice. What we are doing here, setting W1 to 0, this one to 0, is a choice. This simplifies our computation, right? We select this to ensure that A11, I mean, the entry here remain the same, these two. After performing the transformation, A11 is not transformed into something else, but it will remain identical in the result. That's just that choice. And it simplifies. If we fix that A11, we fix and make sure that it will not change when we perform the transformation. So we set W1 to be 0 to achieve that result. Okay, so once that is done, we perform this multiplication and try to see the consequences. Okay, now what do we have? We want H1, that's the first transformation that is applying to the first column, because remember that this is the first column. We don't care about the rest of the matrix, but we concentrate here. If you recall, by analogy, I'm coming back to this. If you remember with Gibbon's rotation, we had a matrix A of this form. A11, A21, A12, A, 2, 2, like that. But when we constructed the G, I, J, theta, when we're selecting the value of theta, we did not use the entire matrix, but we concentrated on what we want to achieve. What we want to achieve is that when we multiply G, I, J by A, we want this to be 0. So we concentrate on the first column. So we use the first column and we apply this G, I, J to that column to make sure that when we apply it to that column, it will 0 the second component. So that's exactly what we did. And it's exactly the same thing we are doing here. We take the first column, we don't care about the remaining. You see, this one, we don't care about the second column of A. We don't care. Once we zero this, whatever happened to this, we don't care. Right, that's exactly the same thing we are doing here. But in our case, we will not only multiply in one direction, but we will be multiplying on both sides. Don't forget. And by multiplying on both sides, if we zero here, you also zero on the other, in the row like this, so that in the process we obtain a tridiagonal matrix. Okay, but that's not, we are not mentioning it, but I'm stressing on that for your information. Okay, so back to our construction. Let me quickly erase, make it clean. All right. Okay, now what do you realize? Because we want this to be transformed into that, and because we also fixed already A11, the only thing we need to do now is to find the expression of alpha. What will be alpha in this process? What will be the expression of alpha? So we have the expression of alpha to determine, and we also have the entries W2, W3, up to Wn to determine. So now you see that we have two things to determine here. This, because we have already fixed W1 to 0, now we can restrict our W, because we can write W to be 0, comma, W hat. This is our W we are looking for. So we don't have anything to do with the first entry because it's fixed to 0. The remaining entries, that's what we call W hat, right? You can see that it starts from 2 to n. So we are dealing with that part. Yeah, maybe I don't need to transpose there because we already have the transpose here anyway, but it's fine. And we take these entries from the second entry to the last entry, we call it Y hat. And these are the new notation that we will be using. So you see that we restrict ourselves to Rn minus 1, right? Rn minus 1. So if we are in Rn minus 1 into our H, because remember that H is a matrix, n by n matrix, right? N by n matrix. So we have something like this. We have this first entry here, first column, first row. It's like that. And this is our H hat. And this is a complete H. So this is our case. So in other words, we are restricting our work from H to H hat and W to W hat, Y to Y hat. So everything now will be restricted to Rn minus 1 instead of Rn itself. Okay, and now this H hat, which is n minus 1 by n minus 1, has all the transformation is given by this expression. So if we know W hat, we have W, right? Because W is, in fact, W hat because the first entry is already fixed to 0. So you see, now we are going to work with a reduced expression. So what I wrote here, this H is what we have here, right? And now you can see that this matrix vector multiplication, because remember that's what we want here, because we are rewriting this. 330 is rewritten here. So we have this times H1 times this first column of the matrix A is the same as this. So if we multiply, you remember matrix vector, matrix vector multiplication. If I take this and multiply by that, this will be the result. You can see it. This into that gives us this. Okay, so let's see. We know that this one will give us a vector, right? Remember, we said that we want A11 to be mapped to A11. That is why in the first column, all these other entries should be 0, and in the first row, all these other entries should be 0. Otherwise, you will not get 811 here. So for this result, imposing A11 in the final result has an impact in the structure of our H1. And that impact is that the first row and the first column of the matrix H1, all the entries there except the diagonal element will be 0. Now, if we take this and multiply by that, you see that A11 will multiply 1. And this Y hat will multiply 0. And consequently, we will get this result. So if we don't impose the 0, 0, 0 there, we never get A11 here. So that's the consequence. So you see that it simplifies already the expression of our H1. Good. Now, the other entries here, you can see that if you take this, we multiply by that, A11 will multiply here, 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 here. You see that A11 will disappear in the process, and the Y hat will multiply HY hat. So that's why we have this result. All right. If you still don't understand, you can take a 5 by 5 matrix and try to do this computation. You will understand better. Okay. Okay, now this is what we get, and of course, remember that we want the result to be equal to this one. Now, what is the next thing? It's just to identify. Identification. This is equal to that, and this is equal to this. So we know already what our H hat, Y hat is equal to, just by identification. Right. So H hat, Y hat is equal to alpha 0, 0, 0 transpose. It comes from there. So this is equal to this by identification. And now the next thing is we know the expression of H hat and Y hat. This is H hat, we put it here, and Y hat, we keep it there and we expand. You know that Y hat times identity is Y hat. And now negative 2 W hat, W transpose into Y hat is this expression. Right. Now we try to expand that expression. Right? And to make things easy, we know already, because this is W transpose, which is a row vector, and this is Y, which is a column vector. Row vector times column vector of the same size gives a number. It's a number, it's not a matrix. It's not a vector, it's a real number. And this real number, we call it R. You see that by so doing, we simplify this expression. This is R. We make our computation easier. So remember that we have formula or equation 331, which is this. Now, if we substitute this expression, we have right hand side, which is alpha 0, 0, 0 transpose, equal to this expression. So if you take this expression, right, we know what our W hat is. Don't forget, this is Y, this is Y. If we subtract this from Y, we have Y hat, this is Y hat. So Y is equal to A11 Y hat. So Y hat start from is A21 up to AN1. That is Y hat. So if we write it here, we expand that, we get this. Right? I hope it is clear for everyone. Look, this, if I rewrite, H hat Y hat is equal to Y hat minus 2 R Y hat from this. And I know the expression of Y hat. Y hat is A to 1 up to A and 1. Now, if I take that here, that would be A this one, sorry, this one is not Y, but this one is W, right? This one, the last one, this last one. From here, that's why I put yellow here. This is this one is W hat. I hope you agree with me, because what are we when we expand this? What do we have? We have this part, this 2 is negative 2 W hat transpose Y hat. Right. Now, this W transpose Y hat is a number. That's what we call R. So you see that we have negative 2R into W hat. So this is W hat. So Y hat minus 2R W hat. Now, I know W hat. Remember, W hat start with W1, W2, W3. Now, if I substitute things together, this will be A21 minus 2W2. That's the first component. The next component will be A31 minus, oh, there's R somewhere here. I forgot to write the R. Minus 2, oh, sorry. Minus. So that will be A21 minus 2RW2. So I will do the same thing. I repeat up to AN1 minus 2RWN transpose. So that is this final result. And that's what we have here. A21 minus 2RW2. All the way up to the last entry, which is AN1 minus 2RWN. So that's what we have here. Okay, so I hope it's clear, that explanation. Good. Okay, so now that we have all these entries, remember, we are equating this with this. So meaning that this first entry is equal to the first entry of the left vector, and the remaining entries are set to 0, right? By identification. Remember, two vectors are equal if their corresponding entries are equal. That's what we are doing here. So this first, so alpha will be equal to this one. So we have that. That's our first equation. Now, 0 equal to each of the remaining entries. So we can write that in a single statement, right? That is, 0 is equal to A sub J1 minus 2RWJ, where J runs from 3. Because remember, for all these entries, the first components are from 3 up to N, and that's what we have. So this is a compact form. Instead of writing everything, we write just this. Now you see now we have obtained an equation that we need to solve. And now the remaining steps here are just to solve this. That's all. Now, once you understand the principle, the rest is just linear algebra. How to solve that? That's just linear algebra until you get that. And you get an algorithm that allows you to solve. So I will not go into the detail of all this linear algebra at your level. You should be able to follow the derivation all the way to here. So the takeaway is this one. We summarize how to get, you see how the alpha, when we follow all this, we solve that system, this one, because this is the system that we are solving. All right. So this is the system you are solving. When you solve that system, you don't need to know these details by heart. Just read to have an idea of the procedure. But the most important thing is this one. So for H1, this is what you get for alpha, the R, because remember we need to know R, we need to know alpha, and all the W's, because W1 is already 0, and the remaining W's are in terms of alpha and R. You can see we have alpha here and we have R there. So they are given by this formula. That is for H1. For H2, we will proceed, because remember that with H1, when we apply H1 to A, we zero the entries in the first column and first row. Remember, symmetricity property will give you 0 here and there simultaneously. Because we multiply here, multiplication on the right, on the left will 0 here. And multiplication on the right will 0 here. So let me write here. This comes from the right multiplication. That is AH1. So that's what produced this. And this one comes from the left multiplication. That is H1 times A. But it looks a bit confusing. When I separate the two like this, you have the impression that we will do this, and then we will add H like this. And how do we put together, right? But remember that when we multiply, here you have two multiplication. You have this one and you have that one, right? You multiply this by that, and the result of that you multiply by H1. That's what I'm trying to say. I'm not saying that you multiply this separately and that separately, and you put the two together. No, that's not what I mean. Anyway, you are clever to understand that. So maybe it will be better here. Ooh. I will just put x like this into H1, where this x is the result of this. Yeah. Okay, so that is it. So this is the first stage. When we compute H1, we multiply, we get these zeros. Now, if we proceed further, that is, if we construct H3, which is H2, A2. That is, we take this result H2, A2, we construct H2 and we multiply A2 by H2 on both sides. Then, sorry. So if we proceed with this multiplication, what will happen? This will be 0. You see. And simultaneously, we will also 0 here. So what happened? You see that the 3 diagonals appear. You have this diagonal, you have the main diagonal, and you have this other diagonal. They will appear, and the other will be 0. Okay, so that's for your learning. I'm doing all that for you to understand what is going on. So as we proceed many times, we'll be creating more and more 0, and the AI that we are constructing will get close to tridiagonal matrix that we are looking for. Okay, I think we'll stop here. I have an idea now of the. Once you understand this, I encourage you to go and read what we will do tomorrow. Okay. Among you, do you have some students who will be doing the presentation, the week presentation? Are there some Hello.
Doctor.
I'm asking,
Mm.
are you aware of the will presentation tomorrow? Will presentation
Yes.
is for you. So meaning that, anyway, I will check the time again, because our class is supposed to start from 8:30 tomorrow. The will presentation, surely, if it's from 8, then I will not be available. I will be recording after the will presentation. And it's also likely, because I owe you two videos, so it's likely that in the meantime, I might also record other videos, right? And in those videos, I will be covering the remaining part of the program. Otherwise, see you on Friday. You are writing, meaning that even Friday there will be no class because you'll be preparing for the test. So if there's no way we will have another face-to-face, I'll only record and post it. Okay, I wish you all the best. God bless you and see you next time.
Doctor.
Bye-bye.
Doctor.
Yes?
I have a question regarding the comprehensive test.
Can you speak aloud, please? Your microphone is low. Can you unmute? I mean, not unmute, but...
Okay, sorry. Can you hear me now?
I can hear you, but the sound is not good and the volume is low on your side.
Okay, let me try. Doctor, I'm saying
Yes?
I have a question regarding the comprehensive test.
Yes, I got you.
Yes, when doctor said the test goes up to QR factorization, it starts from where? From chapter 1?
No. Chapter 2.
The whole of chapter 2.
Okay, let's say yes, the one of chapter 2, yes.
Okay. Thank you, doctor. That's all.
No problem.
Okay.
The aunt and uncle.